Okay, so as you skip through the next few slides down to slide 10, this shows the theoretical efficiency versus compression ratio. So as you see, as you get higher and higher compression ratios, the efficiency of the ideal Otto cycle goes up. This is the ideal cycle, remember, assuming all the ideal assumptions like air is the working fluid, the compression and expansion processes are reversible, which means there's no friction. Obviously, a lot of those assumptions aren't true in the real cycle. So the real efficiency that you would get is much less than that. But the same, much less than this, it presents in slide 10 anyway. But again, this is the ideal case. So you might expect about maybe half of this. One practical limitation that we run into is called detonation or auto-ignition. The higher the compression ratio, the more likely we are to have detonation, auto-ignition. Knocking is another term for that, where our fuel-air mixture will ignite before the spark fires, before the piston's ready to move in the other direction. If the temperature and pressure inside the cylinder gets so high that a pocket of fuel-air mixture will ignite before it's ready to. And so that's auto-ignition. That's where octane rating comes from, or that's why it's important. If you have a high-performance engine with a high compression ratio, you have to use a fuel with a high octane number. Octane is a measure of a fuel's resistance to auto-ignition. If you go to the last slide, there's an example. So let's do this example. It says an Otto cycle with a compression ratio of 7. So that begins its compression. So we've got some initial conditions there at time 1, 90 kilopascals, 15 degrees C. It says the maximum temperature, so that's always going to occur at 3. It's 1,000 degrees C. Utilizing the air standard assumptions, we want to know the thermal efficiency, assuming constant, and then doing variable specific heat. So first we'll do constant specific heat. So we're looking for the efficiency of this engine. Efficiency of any engine is what you want, which in this case it's net work over what it costs us, which for a heat engine is Qn. Now net work isn't that easy to isolate because it occurs, there's work produced from process 3 to 4, but there's work consumed in process 1 to 2. And so the difference of those two would be the network. So rather than look at it that way, we can also take a big picture view of a heat engine and say the network is Qn minus Qout. And each of those occurs in only one process. We can figure out how much heat was required in process 2 to 3, how much heat was rejected in process 4 to 1. So now we're going to use energy balance. We need Qn. If we look at process 2 to 3, that's where Qn occurs. We just wrote energy balance for this a minute ago. I don't know anything about the mass in this problem, and to get efficiency we could divide both the numerator and denominator by mass here, so we could get lowercase Qn minus Qout. So each of these are intensive properties, kilojoules per kilogram. Qn. Okay. So if we do that here, divide by mass, depends on U3 minus U2. They asked us to do constant specific heat first, so we could even go as far as saying that that's CV T3 minus T2. I'll go ahead and do this one. We'll take the specificity of constant specific heat. We'll use that for process 1 to 2 and 3 to 4 when we have to choose constant or variable specific heat there. So U3, U2, it's an ideal gas, only depends on temperature. So it looks like we need T3 and T2. We have T3, so that's going to get us U3. We'll look that one up in just a second.